All right. Thanks a lot for inviting me to give this talk. It's a great pleasure to talk with the data scientist audience about our latest understanding in how we can do better analytics in large-scale video, and how we can make large-scale video analytics much easier. Before we started, a little bit more about myself. I'm assistant professor at ET Zurich. My main research is in computer vision, especially in video processing, 3D scene understanding, autonomous driving, and robotics. And I've been so I did my PhD at Princeton, and I did a postdoc at UC Berkeley before I came to Europe. So today we are talking about large-scale video analytics and why it is very important. What are the major applications? For example, with large-scale data analytics, we will be able to analyze large amount of videos from different, like safety video footage, or with different type of videos from IoT devices. And at the same time, we can there is a rising demand of using video analytics to analyze the 3D information within a video and trying to do additional augmentation. And of course, with a lot of IoT devices deployed at different homes, and especially in the coming years, we will see more and more robots coming to personal homes, and we will see even more demand for video analytics. And of course, currently, the autonomous driving car or the car with driving assisted capability is generating large amount of videos, and so big that we can not even store all the videos in our cloud infrastructure, not mentioning that how we can analyze them with a limited amount of time. And today we are diving into the foundation of those problems and see that how we can build basic algorithms and tools so that we can analyze the large amount of videos without like headache. All right, so a basic problem in those video analytics is multi-object tracking. It is just like for image analysis, we need to detect persons or detect vehicles in order to understand the visual semantics and what's inside the image. We need object tracking to understand that what are the object identities across frames, and use those information as the basics to conduct like high-level understanding. And we will give some more examples. So since this problem is so important, there has been a long study in this area. So before we dive into this area, actually let's jump up a little bit and to see that what is the general situation in computer vision and why we are seeing more and more applications of computer vision in different type of areas. So, okay, so let's talk about the general computer vision problem. And there is actually a top secret in computer vision. People usually do not talk about that because if we say that like the field will be in a shattering status, which is computer vision is already solved. I'm sure this will be great news for a lot of industry practitioners and especially data scientists, so that we can directly use those tools to understand that the information in the vast amount of videos we already have. However, if we ask some domain experts in computer vision, they will definitely frown to the statement. But there's actually some merits in this statement, and the major reason is nowadays computer vision is becoming easier and easier. So for example, if we want to use certain computer vision applications, say object detection, then there are basically several steps. The first step will be just install PyTorch, and then the second step will be find some code on GitHub. Then after we have those code and the basic software installed, we can just download some prediction model ways so that we can use the existing model to build our own data analytics, especially to analyze videos. And it's exactly as easy as that. Let me give you some examples. First of all, there are some very good foundations in computer vision. For example, in a lot of areas, there is a simple example which is end-to-end learnable, and also there will be a large-scale dataset that can train reliable model and develop the model that we can use in real practice. And of course, there is a huge software platform that can support the use of the model and apply application on different datasets. For example, on image classification, we have convolutional networks. We have a lot of network design that can classify the images in fairly high accuracy. And we have internet and also a lot of other datasets that can help us to train classification of different objects. And of course, we also have PyTorch and TensorFlow. Basically, they always use classification as their first application. And also object detection. We now have FastRCN and YOLO. And in terms of datasets, we have COCO and many other object detection datasets in different areas. In terms of software, we have detection tool, or we have other methods like MM detection that can directly tell us that how to use this thinking model to find an object we are interested in, like persons, cars, or even some fine-grained fine-grained objects. But what about multi-object tracking? So multi-object tracking, the story is a bit complicated. Do we know of a simple model that can support a lot of different applications and be always reliable? And do we have really a large-scale data set that we know of, and people will always think of it when we want to train or test our algorithms? And what will be the software platform to help us utilize those APIs? So, well, before us answer this question, let me give you some quotes. Here is a real quote from a reviewer when we submit our papers. Like he said that existing tracking methods has a lot of hidden knobs and other complexity, and therefore he was demanding more details in our method description to explain why our method is effective. And also, I consult some very renowned CV professor. Your complaint is MOT datasets are very small now. We can easily use graduate student descent to get better results instead of having real knowledge into the tracking algorithm itself. And if we ask, say, engineers or people who really need to use object tracking, usually the answer is all the methods usually work the best. And to understand why is the situation and what will be the pathway to build a good foundation or make the large-scale video analysis easier. So let's look at what are the current algorithms are doing. First of all, currently when we do tracking, we mostly using tracking by detection, which means we will first locate and detect the objects we are interested in. Then we will try to propagate those information across different frames. For example, when we have frame t and frame t+1, when we want to propagate the information from t to t+1 and build association, we will first use some motion information, say either trying to assume that the objects are stationary or try to propagate the object based on some constant velocity. Then on a new frame, with the motion information and some appearance features, we can build some initial association score. And given those association score between each pair of objects on two frames, like on frame t and t+1, we will do some post hoc optimization. Traditionally, we have been using concurrent matching algorithm to match the objects across frames. And nowadays, a lot of people are trying to use graph neural network to learn this optimization. Okay, so let me give you an example of this process. For example, here is a video that we commonly use in the driving scenario. You can see that this is actually a very crowded scene. And on this scene, we can see that there are cars driving by and the people walking around. And on the first frame in the current algorithms, we will first detect all the objects. Then on the new frame, we will detect all the objects again, let's say all the persons here. And then we will propagate the object from the last frame, build some initial association based on the propagation, and then use some optimization methods to find the best matching between those two groups of bounding box. Okay, so this is the basic overview of the current algorithm, and you can see there are a lot of different steps and components in this framework. And the first question here is, does it need to be this complicated? Can we make these methods as simple as possible so that we can easily use those methods and those methods can be even more robust? To understand that, let's first play a game. So here we are seeing the first frame again, and say we are very interested in those 4 persons. Then instead of propagate those 4 persons into the next frame, let's first put those 4 persons aside. And then here is the next frame. In this game, I will just ask you some simple question. And you can answer this question in your mind. And because I'm sure this is very simple to you, I will just review the answer. The first question here is, what will be the color? What will be the identity of this bounding box? I'm sure you can tell me it's red. And what about this one? It's also easy. It should be blue. About this person, this is a little bit tricky because if we look at the bounding box on the left, this person actually appears in 2 bounding boxes, but we know that the person only appears as a foreground object in the yellow box, and therefore this is yellow. And what about this person? As you can see that even though this is also a person, but it does not match, there is no match for this person. And then for this person, of course, this will be green. Okay, so with this small thought experiment, I want to ask you 2 questions. When we do this association, do we actually use motion estimation? Which means that do we actually try to propagate the objects to the next frame based on their location? And the second question is, did we actually do association optimization? I'm sure the answers are no. We do not try to propagate the object to the next frame, and also in our mind, we just do nearest neighbor match and or more like object finding instead of trying to find the global matching. And the global matching can be so complicated in this scene that there can be like more than 100 edges or candidates to compare. That will be too much for us. And therefore, so intuitively, when human to do the tracking task, we only need object detection and appearance association. And therefore, when we come back to our original question, whether we can make this tracking pipeline simpler, then the real question here is, why doesn't the appearance model provide enough information in the current tracking methods? And to understand this question, let's first look at what are the existing methods are doing in order to learn appearance similarity or trying to associate objects based on appearance. So here we have a pair of images, say they are adjacent image in a video, and then we have 2 objects on those 2 frames. And as you can see, when we want to learn that what will be the good association between those 2 objects based on appearance, we will first extract the bounding box, say extract from either the image or trying to extract the bounding box from the high-level features. Then we will try to say, okay, here is the correct match from our ground truth tracking set. And from our ground truth tracking set, and then how we can match them, we can use triplet loss or binary loss to learn that what will be a good matching based on appearance. Essentially, we are just using some deep learning like models, trying to learn the embedding of the objects so that the same objects can always have the same embedding across different frames. So what is missing in this process? First of all, on these 2 images, there are actually a lot of other possible bounding boxes that can be detected as the true bounding box at the testing time. But those boxes can be a little bit shifting from the ground truth, However, we know that if we do not consider those bounding blocks, they can have very different embedding from the original ground truth bounding blocks, just because the plateau of a deep learning embedding is very bumpy and also very discontinuous. Therefore, like all the bounding blocks similar to the ground truth bounding blocks and have very big overlap are not considered in this similarity learning. Another thing is we are not considering a lot of bounding block ground truth, a lot of background bounding blocks that may look like the foreground objects. For example, the red box may look like a black car and can actually confuse the model. But in training time, we do not consider those areas. Based on those observations, we propose a Quasi-Dense matching. It's exactly the matching methods based on our observation. Instead of only using the ground truth bounding box, we extract the outbox that may look like an object even at the training time. And then instead of only learn to match between the ground truth bounding box, we actually learn to match between all the possible box on different images. And here, one tricky thing here is for the objects that are for the bounding box that are around the ground truth, but without correct labels, what we can do with them. We can, based on the overlap of those boxes with the ground truth, to assign some pseudo labels. For example, if a possible region has, say, like high IOU, like intersection over union with the ground truth bounding box, then we say that okay, that box represents the same identity with the ground truth bounding box, and then we can find their match on the other image. Then at the training time, we can use contrastive learning to learn that how we can find a good similarity embedding that can match not only between the ground truth bounding box, but also between all the possible regions on each image. Okay, to implement such an idea, we can directly utilize an existing two-stage pipeline. Say here, this is a standard pipeline from FastR CNN. On this detection model, we have some backbone like a ResNet 50 or ResNet 101. And then from the backbone, we will extract some regions based on region proposal network. And then with those regions, each region, we will do a further bounding box classification and location regression. We can directly reuse those proposed regions in Quasi-Dense similarity learning. So the simple operation here is we can add additional head, like we call embedding head or similarity learning head, to learn that how to match from the proposed region to some feature embedding, as we discussed. And then when we have a lot of candidates, we will match all of them and use contrastive learning to learn that what will be the good embedding to figure out the right correspondence. So as you can see here, this pipeline is not more complicated than object detection. It just add another embedding head on top of the existing object detection region proposal network, and then use contrastive learning to learn how to learn the embedding or how to learn the weights within the embedding head. And at the testing time, we also do not need to use additional tricks to do object matching. Besides using object detection to detect all the possible vehicles or objects of interest on each image, we can also pass the detect all objects into our embedding head. And then instead of using motion queue or post optimization, we just directly search for nearest neighbor within this similarity embedding space. Then the associated bounding box can be directly treated as tracked bounding box. In the real tracking pipeline, even though that we can do the nearest neighbor search, but those are the candidates we use in order to do the search. On the new image, we have all the detected bounding box as we described. But from the previous frames, we have different type of detected objects that we want to build association. There are checklists that we have been tracking for several frames, and also some vanished checklists and some backdrops that can potentially confuse the model. So again, with our idea of building the quasi-dense matching across frames and use that with the existing two-stage object detector, we build a model that have the similar complexity with the existing detection, just additional head to embed the detected objects into a space that we can directly match similarity with nearest neighbor. But even though this is very simple and does not give you additional overhead in object detection, we find that on some small datasets like MOT17, our method can perform very competitively. So as you can see, even without additional training data, our method can achieve better results than the method you may be commonly using. And even compared to some recent methods, like with similar backbone and model complexity, our methods also perform dramatically better. And here is a visualization of how our method works. You can see that even in this very complex scene, our method can perform very reliably and track the person even though there is very complicated occlusion and reappearance patterns. Okay, so one problem with the method, with the existing evaluation, is so the benchmark we are using, which is MOT17, only have 20 sequences for training and testing. So it's very hard to imagine that we can learn very reliable tracking only from 20 sequences. And therefore, to understand how we can perform tracking in general scenario, we have been working on a very large scale dataset called BD100K. And BD100K is still the largest open driving video dataset. As the name suggests, it has 100,000 driving videos, accounting for more than 1,000 hours of driving experience. And the dataset covers different, very diverse scenarios, like different weathers, different time of the day, and also different driving scene type. On top of the videos, we also provide a large amount of labels, like at different levels, like including image level label, lane marking, driver area of the detection, panoptic segmentation, as well as tracking of all the objects, both in terms of funny box and segmentation. And in addition, we have also provided all the trained, a lot of trained models on those tasks released in our repo. Currently, we have more than 100 models ready for use. And back to our discussion of tracking. So in terms of tracking dataset, our BD100K dataset provides like 1 magnitude bigger tracking benchmark compared to the existing popular benchmark that we are using. And here is a demo that on our BD100K dataset using quasi-dense tracking. And you can see that even in this complex scene, our method can work quite well. And even in some tricky scenarios, say this person is about to disappear in very far away region, but when it reappears, we can still track the person very reliably. In addition, when we drive down the street, we can see that there are a lot of vehicles on the other side of the street that are constantly occluded by the trees. But our model can still track those objects very reliably. And remember, this is only based on appearance feature without turning to additional motion priors and the post-hoc optimization. And here is an example running on highway. And of course, with the large amount of data we have, and also the powerful tracking methods, our methods can also work on like very challenging scenario, like the night scene. You can see that there is a rider at the beginning of the video. And even though that's very challenging, but our method can still locate and track those objects very reliably. So if I tell you that our method performed best on B200K, that may not be very convincing. But at the same time, there's also another dataset called a WIMO Open Dataset, which also provides a very large-scale tracking data. And you can see that on this large-scale tracking data, our method performs significantly better than the competing methods. And even though that those, like the other methods, are also provided by a very professional team on the same dataset. So one afterthought here is, you may ask, is appearance similarity really enough? The answer actually is, it may not be perfect, but it may be more than enough than we might imagine. For example, when we consider this person, the similarity embedding of this person actually consider a much larger region. And with this region and with this representation, it can also encode some location information. And the network can learn how to use those location information when it's become necessary. So given our powerful tracking method, we can do a lot of high-level application. Here I will give you two examples, one for 3D tracking, the other for segmentation tracking. So the task of 3D tracking is given a sequence of monocular images, like only the images with a lot of LiDAR data. And our goal is to perform tracking in 3D by estimating the association of the objects on 3D and also estimate their 3D trajectories. So based on Quasi-Dense tracking, we can actually build a very simple pipeline. First of all, we just locate the objects on each image, and then for the feature extract for each object, we now, instead of only regressing the 2D location and the class, we can also predict the depth of the objects and also their rotation angle. Then when we have multiple images, we will try to match the objects together. And then when we have even more images, we will be able to project the objects into 3D and estimate their trajectory and also their motion information in 3D. So it's worth noting that 3D motion information will be critical for certain analysis. For example, in autonomous driving, we will rely on those 3D motion information to predict where the other vehicles will be in the future in order to have a safe planning for the Eagle vehicle. And the 3D motion can also have a lot of other useful priors or useful information for us to build more reliable tracking. For example, when we track different objects, sometimes the objects can disappear. And in 3D, since we can estimate their location very reliably, then we can just keep sliding the objects across in the 3D space and see that whether it will reappear in a new frame. Another thing is we can also consider order as a prior for association. For example, we know that when we have a sequence of depths between objects, then in the new frame, they shall not change a lot, or they should not change dramatically in a very short time frame. And with this simple pipeline, you can see that our method can actually perform quite well, even on very challenging street. For example, here is a result on WIMO dataset. And again, we are only using the monocular video. We are not using the LiDAR data as the inference time in order to predict 3D bounding box. We can see that our methods can track the objects very reliably, both in 2D and 3D. The top-down view on the right gives you some sense that how accurate our 3D trajectory estimation is. And of course, our method can also work in the dark scene. So again, we achieve all those results without turning to like a 3D LiDAR, or we are only using the monocular camera information. So another thing is for segmentation tracking. Since we are almost running out of time soon, so I will only provide a short overview about our tracking methods. So if we directly use Quasi-Dense tracking to associate 2D objects, then we can directly use the mass RCN on top of the 2D detect 2D bounding box to do object segmentation tracking. But that naive method does not consider the temporal information, or it does not use, say, the track the objects to enhance the segmentation of the same objects on a new frame. And therefore, we build an additional module called the prototypical cross-attention networks, so that we can extract some prototypes from the previous frame. And after we associate the object together, we can use those prototypes of the previous frames to remember what the object's information can be and have a richer representation for the object shapes. Then on the new frames, we can use those richer information together with our existing segmentation model like master RCN to improve the segmentation quality. And we find that in the end, we can actually achieve quite impressive segmentation results. For example, this is a demo on B200K. So we are also supporting the segmentation tracking, both for training and testing on B200K dataset. And you can see that we can track the object segmentation quite reliably across frames, thanks to both our Quasi-Dense matching to associate the objects and our new segmentation tracking methods to find out the accurate segmentation across the whole video. And of course, our methods can also work in the dark scene, thanks to the training data on B200K. And you may ask, so why is the online information so important, and why we should use them? Here is this example will give you some clue. So here we are doing this thing of segmentation tracking on YouTube data. So okay. So you can see that with our online tracking methods and the online cross-attention, our method can achieve much better consistency across the whole video. Okay, so if you are interested in any of the methods we have developed, you can check our method project webpage. So if those are a long URL that will be hard to remember, you can just simply remember that all of our projects are on this URL with .xyz. And we have also released the open source code for the methods that I discussed. So in addition to the software that we have already released to reproduce the results and run the results on new sequence, we are also working on a new library for this dynamic 3D scene understanding, so that we can make those methods easier to use. So we are working on a library with flexible API for those visual tracking algorithms. And partly it's driven by our internal research need, and also we believe that such a library will have broad influence in the industry as well, especially for large-scale data analytics. So in order to achieve its full potential in using the software for the normal video analytics task, we have been spending a lot of efforts to polish the code quality so that it can have decent efficiency and also with very readable coding style. And in addition, even though we are using Python, mainly using Python to implement the algorithm, we are having strict typing and 100% test coverage, so that we can make it really clear how the library is supposed to be used, and also make sure that each component is well tested before we use them in the broad set of applications. So we are still working on that, and we will release them soon. If you want to receive updates about our progress, feel free to follow me on Twitter, and we will for sure give you more updates about our progress, as well as additional new methods that we have been developing in this area. Okay, So in terms of large video analytics, in this talk, we discussed that a simple model, like we demonstrate the case that tracking can actually be as simple as detection with Quasi-Dense tracking and Quasi-Dense similarity learning. So we hope that with our simple model, the tracking method can be as easy as object detection for video analytics. And in addition, we also provide a large-scale dataset, B200K, that you can directly download today, together with a lot of annotations for different type of tasks and for different type of video analysis. At the same time, we have also released the model tool for B200K that provide more than 100 pre-trained models now, so that you can directly start with those models and the results. And at the same time, we also welcome you to contribute your own results and models to our repo, so that the whole community can share our results and benefit from each other. At the same time, we are also working on a software platform that can make the algorithm easier to use on different type of data. Okay, with that, I would like to conclude my talk. And if you have any question, I'm happy